thanks everyone. Is that too loud? Okay, it just sounds loud. I'm going to be talking about WarpStream today, and going beyond tiered storage and basically rebuilding Kafka from the ground up to have no local disks. Before I get into the no local disk part, though, I want to spend just 1 second talking about tiered storage and why tiered storage is valuable. So tiered storage was added to Kafka relatively recently. And the main reason and the main value for it is that cloud disks are really expensive. So if you look at these numbers on the right, if you look at an EBS volume, GP2, they're about 10 cents per gigabyte pre-replication. If you're running your cluster with 3x replication, you're paying 30 cents per gigabyte for these volumes. Data stored in S3 costs 2 cents per gigabyte post-replication, right? The data in S3 is already replicated. So compared to like 3x replicated EBS, it's already 15 times cheaper. You can play around with these numbers a little bit, right? You can do double replication instead of triple replication if you like living on the edge, or you can run local SSDs, and that brings down the cost a little bit at the expense of making operations a little bit scarier. But the economics just don't really change. If you're running in the cloud environment and you want to store a lot of data, eventually that data has to be in S3 if you want it to be cost effective. And even with relatively low volume workloads, if your retention is really high, EBS or local SSD costs can easily dominate the cost of a workload. So tiered storage helps a lot, makes things a lot better, especially if you have long retention workloads. But it's not enough to really, I think, make Kafka really easy to operate in cloud environments. So what we set out to do with WarpStream is just get rid of the disks entirely, try and make Kafka as stateless as possible. And one of the big reasons for doing so is it just makes operations way easier. A lot of you here have probably run open source Kafka or self-hosting, just how much tooling and automation it takes to do that in cloud environments. You have to deal with consensus, you're dealing with topic partition leaders. If you scale the cluster in and out, partitions have to be balanced. You have to wait for data to be copied, just a bunch of stuff. Balancing is always tricky. There's just a bunch of stuff that goes into running open source Kafka by yourself, basically. And a lot of that complexity just comes from the fact that the brokers themselves are stateless, and that when you produce data, it has to be written to specific brokers and replicated to other specific brokers. And if you could move that to remote storage, you just wouldn't have to deal with that anymore. The other reason that getting rid of the disks entirely was one of our design motivations with WarpStream is that even if your retention's short, you're only keeping data for 4 hours, 8 hours a day. If you're writing at really high volumes, easily 80% of the cost of your workload, if you're running a 3AZ triply replicated Kafka cluster, is just copying data between availability zones, right? So if you look at this, okay, it's kind of hard to see on the screen, but 2/3 of the time your producer is going to be writing to a topic partition leader that's in a different availability zone, so you're playing interzone networking there. Then once the data reaches the topic partition leader, it has to be replicated to 2 other brokers that are running in different availability zones. You're paying for interzone networking there. This diagram is showing a perfectly optimized Kafka cluster where fetch from follower is enabled and the consumers are reading from followers to avoid interzone networking. But even that perfectly ideal scenario that most people don't manage to get to because they work for large companies, they have multiple VPCs, the consumers run in different environments, right? Even that perfectly ideal scenario, it costs 5.3 cents to send a gigabyte of traffic through this setup when it only costs 2 cents to store that data in S3 for a month. And so the economics in cloud environments are just not in your favor of manually replicating data yourself. So zero disk would be better. If we could achieve that, we'd get drastically reduced operations, drastically reduced costs. And so that's what we try to do with WarpStream. So the idea with WarpStream is we replace the stateful Kafka brokers with things we call agents. You can think of agents as virtual brokers. They're just basically really thick proxies that sit in front of object storage. They handle buffering and batching of produce requests, and then they handle caching for fetch requests. And the way this works is you deploy them into your own cloud account. You split them over multiple availability zones. And because they're stateless and any agent can write data for any topic partition, you can always zonally align your producers. So your producer is never going cross AZ. Your consumers are never going cross AZ, no matter how your topic partitions are configured. You don't need to enable fetch from follower. And the other big thing is that the agents never communicate across zones. So when you produce to one agent, it doesn't replicate to 2 follower agents and 2 other availability zones. It just writes to object storage directly. And then when that data needs to be read in a different availability zone, it's read through the object storage layer. So we use object storage as both the storage layer and the network layer. And that allows us to bypass basically all of those interzone networking fees. But you get still all of the same durability guarantees, right? When a producer writes to an agent, it gets buffered for a while. It eventually flushes a file to object storage. That file gets committed into a metadata store. I'll talk a little bit more about that in a second. And only once those 2 steps have completed do we then acknowledge the request back to the producer. So if you get an acknowledgement in your client, the data has been durably persisted to object storage. So the durability guarantees are still really strong. The penalty you pay, obviously, is latency. It has higher latency than using a traditional Kafka cluster, and I'll talk a little bit about that more soon. So obviously, if we can make every system stateless, that would be really cool and magical, but like, how do you actually do this, right? Before I dig into like the exact details of how it works, the thing I want to talk about a little bit is just like the economics of object storage. When we set out to kind of rebuild WarpStream completely around object storage, we knew that we couldn't just take some design that we thought was good and then rent some EC2s and pay for object storage and hope it would work out. Object storage is going to be like the dominating factor for the cost model of WarpStream, and so we have to optimize the storage engine around the economics of object storage. And the key things to kind of know about using S3, and this applies basically in every cloud. Put requests are really expensive. You're paying to write every file that you write, basically. And then you pay for get requests. They're 10 times cheaper than put requests, but they're still, if you do a lot of them, it'll add up pretty quickly. But storage is really cheap, right? I talked about this earlier, 2 cents per gigabyte, basically, compared to, 15 times that for triply replicated EBS volumes. And most importantly, there's no concept of cross-AZ networking, right? You can write data to S3 in one zone, you can read it in another zone, and there's no networking fees applied to that. And when you make a GET request, you can read as much data as you want for the cost of making that one API call. So if you're going to read some data, you should make it worthwhile and read a lot of data. And so kind of with these numbers in mind, we designed WarpStream storage engine completely around minimizing the number of put requests and the number of GET request operations that we do. And because networking is free and storage is cheap, there are some kind of obvious design trade-offs that fall out of that. So basically, if you can make trade-offs around space amplification to reduce costs elsewhere, that usually ends up being a good trade-off. And as you'll see, WarpStream, the compaction system kind of looks like an LSM. And the reason that's possible is because, again, networking is free. So reading and writing data back and forth from object storage, once or twice to compact it and make the data more optimal, it just doesn't really cost you that much as long as you don't do too many S3 puts and gets to do that. So step 1 for doing this was eliminate the concept of topic partition files. Having files per topic partition makes a lot of sense when you're running on SSDs or if you have a big page cache and you have a spinning disk. But when you try and do that with an object store, basically, if your workload has thousands of partitions or tens of thousands of partitions, and you're trying to write little files for each of those topic partitions constantly, the worst case scenario basically degenerates to writing one record per put request, which is just like insanely expensive. So this model just doesn't work. You need to decouple the number of partitions that you have from the number of object store API requests that you're making. And the way that we accomplish this in WarpStream is we just make files that contain data from multiple topic partitions. This has a bunch of implications. You're going to see I'm going to kind of slowly pull on the thread of the implications of this design choice. But there's basically no way around this. If you want to use object storage as the primary and only storage, you want to have reasonably low latency, and you want to have low costs, you have to do this. There's no other way. And so the way that this works in WarpStream is a client connects to an agent. In practice, you have hundreds or thousands of clients doing this. They get routed to an agent. They send batches. The batches get buffered in the agent for up to 250 milliseconds, or until we have 8 megabytes of data. That file gets flushed to object storage, and then the fact that that file exists gets committed to the metadata store. and then we acknowledge the request back to the producer. So this introduces, that means your producer latency is going to be higher than it would with Kafka, but each agent is basically only making one file every 250 milliseconds. And if you do the math on that, it's very cost effective even for extremely high volume workloads. Now it does cause a floor on the cost, right? Like the minimum cost of a WarpStream cluster that's doing this with even 2 or 3 agents, it's going to be at least a couple $100 a month. But as you start writing more and more data, it gets more and more efficient. The second thing that you kind of have to do is you have to separate data from metadata. So if you think about how it is with Apache Kafka, you're like, I want to read some data from this topic partition. You ask the cluster who the leader is. You go to that leader broker or one of the followers, right? If you're using fetch from follower, there's a file on disk. The data is all laid out nicely and contiguously, and you just start reading it. With WarpStream, because there are no leaders and you have multiple agents concurrently writing data for multiple topic partitions, you have to figure out basically the ordering of the data. Now you can imagine that we kind of elect leaders for agents, and then they get to write some data for a topic partition, and then the next one gets to write, and you can kind of sequentialize it that way. But that doesn't work when you have a really high latency storage medium like S3. The way to get high throughput out of object storage is you have to write data with massive amounts of parallelism. And so we needed all of these agents to be able to flush data to object storage concurrently and with high throughput. And so the way we do that is we've separated the act of writing data to the storage medium and determining the order of that data. So in Apache Kafka, the data basically gets ordered in memory and is just dropped to disk. With WarpStream, files get flushed to object storage, but the final ordering of which batches, two files get flushed independently, whether this batch precedes that batch is not determined until the metadata for those files is committed to the metadata store, and then the metadata store essentially can serialize those operations and assign offsets to the files. And so that's another thing that you have to kind of do, basically, once you take this approach. And so you essentially have a metadata store that kind of acts as the sequencer for the entire cluster, instead of having each broker do it for each topic partition. But you can still scale that really well because the work that the metadata store has to do is just tracking numbers. Next thing you have to do once you do that is you have to figure out how you're going to read the data, right? So if you have thousands and thousands of partitions, and you have a bunch of clients trying to read a bunch of data, like I said, the data is going to be kind of scattered over different files in object storage. But the thing that's kind of interesting about how Kafka consumers work is in the kind of normal case, you have a bunch of consumers. They're all trying to read the live edge of some set of topics, right? And so what we do in WarpStream is we form essentially a distributed file cache so that we can basically create leaders, quote unquote. They're stateless, but if one goes away, you can just refill the cache. But we elect essentially agents that are responsible for specific files. And then anytime a client needs to read data for a topic partition batch that's stored in a file owned by a specific agent, the request gets basically proxied to that agent. What that allows us to do is essentially coalesce all the IOs for the same file together to make really nice, large, contiguous IOs against object storage, and then we can build in-memory caches. So to make that a little bit more concrete, because it's pretty confusing, so there's that file that's highlighted at the top in the object storage section. That file, the kind of quote-unquote owner agent, is agent 2. And so what we see here is we have 3 clients, each connected to 3 different, and this is all happening in a single availability zone. We do this entire process again in each availability zone to not have any interzone networking. But we have 3 clients, each one connected to a different agent, and they're each reading a different partition. So the blue one's reading partition 19, the orange one's reading partition 2, and the green one's reading partition 3. It just so happens that these 3 clients, they're trying to read batches that are located in the same file. That may seem like, how often does that happen? But it actually happens basically 100% of the time, because in practice you have hundreds and hundreds of fetch requests, and what the system does is finds all the ones that are being routed to the same area and ensures that happens. So the blue client is trying to read 1 megabyte of data for partition 19. It gets routed to agent 2. It turns out that block of data is not in the cache. So agent 2 goes and does a request to object storage to read a 4 megabyte block. So not only does it read the blue block of data, but it also reads an additional 4 megabytes ahead and captures essentially the orange data and the green data that the other 2 clients need. Now, the orange client comes in either concurrently or after the fact. And if the blue block hasn't been loaded yet, it just knows that it's being loaded and it waits. So you get kind of deduplication. If you ever used like caffeine in Java, it's kind of like the behavior of a loading cache. And then you can imagine even later, after the data has been loaded, the green client comes in, sees that that entire block of data has been cached in memory, and then it can just read the little bit of data that it needs directly out of memory. And so basically routing all the requests to specific agents that are responsible for specific chunks of data. And the net effect of this, if you do it well, is you basically only have to read every byte of every file that's written once in each availability zone, and you can do it with almost exactly one GET request for every 4 megabytes of data that you need to read, or for every file that's written. And if you do the math on that, and I'll show some math later, that ends up being extremely cost effective. So that's how we introduce data locality for live reads. Of course, that only works if all your consumers are reading like the tail end of the data, right? That's not always the case. So for example, if you have a lagging consumer or you reset the offsets, you're gonna have one consumer that's just reading a completely different set of data, and there's no opportunity for shared I/O, right? So if you look at that diagram on the right where it says shared I/O, that's basically I collapsed that entire slide before right into there. And the slide on the left is basically showing the lagging consumer who has no opportunity to share these I/Os with anyone. So this is a problem, right? Because if you think about it, if every time you have a lagging consumer, they have to go and basically make tons and tons of tiny I/Os, then not only is it going to be expensive, but it's going to be slow. Because you're writing one file every 250 milliseconds for every agent, and over time that adds up. And so the way we solve this is with compaction. Very similar to like a data lake system, right? If you have a traditional data lake, you write lots of small files to keep the ingestion latency low. And then over time you compact those small files into bigger files so that queries are more efficient. So WarpStream does the same thing. And you can think of basically this system as just being there to deal with the fact that the live edge of the data has not been compacted yet. But once the data has been compacted, we can just rely on the fact that we've reorganized the data to be efficient, even if only a single client is reading a single topic partition. Compaction is really simple, right? You take a bunch of small files, you shove them together, you make a big file. And what that does is it takes, if you had 32 input files and they each had one batch of data for partition 2, you end up with one output file that has one really big batch for partition 2, and that makes the historical reads for the lagging clients really cost effective and fast. Of course, Kafka also has support for something called compacted topics, which is not the same as like the compaction that WarpStream does by default. And the way compacted topics work is basically you have a topic and every record in Kafka has a key, and then when topic compaction runs, it scans the log, it finds records that have the same key, and it just like deletes the older versions of the key, and only the latest version of each key is retained so that you can have smaller topics if you're writing the same keys over and over again, right? And so this is actually a pretty hard problem to solve, right? If you're relying on a tiered storage system, because like one of the reasons that it's like straightforward to implement, not that straightforward, but one of the things that makes implementing tiered storage in regular Kafka easier is that basically the segments are usually immutable, right? You just move them to object storage and then they don't get touched again, and eventually you delete the whole thing. As soon as you introduce this concept of compacted topics, you're rewriting data over and over again, and how do you do that efficiently and track that in object storage, right? And so we were like, okay, WarpStream already does compaction for regular topics. We need to support compacted topics. How hard could this possibly be? And the big thing for us to figure out with our compacted topics implementation is that you can't like in a regular Kafka setup, you have a segment file that's on disk. You can read to the end of a file, then seek back to the beginning, and doing stuff like that isn't too expensive. But with WarpStream, we needed to make sure that we could basically run an algorithm for compacted topics using like the minimum number of GET requests to do that. Like we couldn't afford one GET request per topic partition. It needed to be like O of n with the number of files, not the number of partitions. And so the thing that you basically need to do though with a compacted topic, when the algorithm is you basically need to scan the log, look for keys, like build an in-memory map of keys to offsets. And then as you're building that map, you can figure out that for each key, the latest offset is like X. And then you go through the files again, and as you're processing each record, you check the map and you say, is this the latest offset for this key? If it's not, then you just drop that record, and if it is, you write it out, right? Because you want to be able to process You can keep all the keys in memory maybe, but you need to process all the like values for the records in a streaming fashion. Otherwise, you're going to use a ton of RAM to do this. And so this is an example of a segment that's really hard to process, right? Because the two records are very far in what I call like key space. There's like 10 million different keys that separate these two keys. And so that's like 10 million different keys that have to be tracked in memory. And so that'll be like a little bit more difficult to deduplicate. And here's an example of, these two records are very far in offset space, right? Offset space. There's 10 million records that separate them, but the number of unique keys that separate them is really small. So the amount of memory you need to track this is not that big. So it's easier to deduplicate. You need less RAM. And then the way that we do this to minimize the number of GET requests that are required is we start every compaction. So there are multiple files participating in a compacted topic compaction, but I'm only going to show one input file because it doesn't really change the algorithm. So you have an input file, and you open two streams to the beginning of that file. And then what you do, you have like two pointers, and you advance them independently. So the blue pointer advances, right? So it reads from the beginning of that partition to the end of it. And by the end of it, it has built an in-memory map between every key and the latest offset for that key in memory. Then we can advance the green pointer, and while it's processing each record, it can consult the map that the previous pointer built and decide which records it's going to write to the output stream. And so that allows us to process even a file that's like 256 gigs and has data from thousands and thousands of partitions with a very small amount of memory, because we're only keeping in memory the hashes for the keys of a single topic partition at a time, and the values are all processed in a streaming fashion. Sorry, it was like a mouthful. But we have a whole blog about this on our website if you want to go into more details. It's a little bit hard to explain with just the slides. The point is you can make two GET requests and process the entire file, as opposed to like, the way that regular Kafka does this is just reads to the end of the partition and then it just seeks back again, right? And if we did that, that would be like ultra expensive because you'd be making essentially two GET requests for every topic partition in the file. And we always have to make sure that everything we do is O of n with the number of files or throughput and not the number of topics or partitions. Just to give you an idea of like the trade-off between interzone networking and object storage fees, and I'll talk about latency in a second, but like if you're writing a gigabyte a second of data compressed to 3 availability zones using like cloud sticker prices, you end up spending like $1.68 million per year on interzone networking. That's how much cloud networking costs. Whereas like the equivalent, because of how WarpStream's object storage like optimized storage engine works, we introduce object storage fees that weren't there before, but they're drastically lower than what you're paying for interzone networking. Now, of course, it's a catch. It's not complete magic. The trade-off you make with this design is that we have much higher latency than a traditional Kafka cluster. So the P99 producer latency, and you can vary this with how you tune the cluster, but you need to expect between 400 to 500 milliseconds of P99 producer latency. And then the graph is showing a pretty well-tuned cluster with regular object storage and the default settings. P99 producer to consumer, you're going to end up in the kind of 1.2 to 1.5 second range. For a lot of workloads, if you can get massively reduced costs, massively reduced operational burden, this is a good trade-off, but it is a trade-off. And then the other thing that's kind of cool is that some of you've heard about this. Amazon recently released support for S3 Express one zone. Azure already has, I forget what they called, but they have like a low latency blob store thing. And then I think GCP just announced that they're working on theirs as well. But with S3 Express Zone, we added support for it, and we can actually get P99 producer latency as low as like 150, 140 milliseconds. And we still get the same durability as, maybe not the same exactly, but you still get good, basically resiliency to a zonal outage by writing to a quorum of single zone S3 Express buckets. So there's 3 buckets and you write to 2 of them, then you know that even if one of those zones is down, you'll still be able to read your data. Within a single zone, S3 Express, it does, it makes sure your data is replicated within that zone. And the cool thing is that there's 2 trade-offs with S3 Express one zone. It's way lower latency, it's way more consistent, but it has way higher storage fees. It's only in one zone, and you have to pay beyond the first like half a kilobyte of data that you write and read. You're paying essentially for throughput, kind of like interzone networking. And so with the quorum thing, we can work around the fact that it's not resilient to a zonal outage. the way we work around the fact that the storage fee is way higher is that, I was talking about how WarpStream is constantly compacting your data. So we land the data from the produce requests directly into S3 Express 1 zone, and then just get immediately copied, like within 10 seconds, into an S3 standard bucket. And so you get kind of low latency ingestion of S3 Express, but the low storage costs of S3 standard. But the catch is that it costs more money. And so if you do the math on this, what it ends up being is about the same price as interzone networking, depending on how S3 Express ones. Yeah, they pick the numbers very carefully. They know what they're doing. And so, but the cool thing about this is you can just have one architecture, right? You can just have one stateless system. You crank the knob this way, you get really low cost and higher latency. And you crank the knob this way, you get lower latency and higher costs. But you don't have to like switch databases or systems. So you can just use one architecture, which is nice. I guess I talked faster than I expected because that's it. So I can do questions now.
Hey, Richie, great talk. With S3 Express Zone, do you also get better producer to consumer latency? I would imagine, especially for like the tail read situation where that presumably matters.
I guess I didn't include it in the slide, but what we measured was just under 400 milliseconds from producer to consumer at the P99. All the numbers here are P99s.
Thank you, great talk. For the cache lookup, you said that one agent can look up the cache from another agent. Like, how does the routing work? And when agents get restart, like, do you just cache miss? And
are you talking about this one?
Yes.
Yeah. So one zone is not the cache is per zone. So if you run the software in 3 availability zones, then you have essentially 3 distinct hash rings. So the agents never communicate across zone. That's baked into the design everywhere. In terms of what happens when an agent goes away, you just get cache misses. The agent, agent 3 is trying to talk to agent 2. Agent 2 disappears. It'll get a failure. It'll try on the next node in the ring, and the next node on the ring will just go fill its cache from object storage. So it'll take it'll cost a little bit more money for like a couple seconds, and you might get like a latency penalty until.
My question is like, for example, here, agent 3, how does agent 3 know the cache is on agent 2?
Oh, so our service discovery system tells each agent what other agents are running in the same availability zone as them, and then we just build a hash ring in.
I see. Yeah. Okay.
So really, it's very simple. Nothing fancy. And it's just reading. The load is each agent is responsible for different 16 megabyte. Like the thing that we use to hash, like which agent we're going to, is a 16 megabyte range of a file, so the load is extremely evenly spread.
Sorry if I missed this. Is there a significance in having the concept of partition here, or is it just to remain compatible with Kafka?
The partitions are definitely like a physical thing in our files. So like if you look at one of our files, they look like this. There's like batches for individual partitions. There's within partition, we guarantee an ordering. So there's still physical things that they have the same exact implications they do basically in Kafka. Maybe one difference is that you could write 2 gigabytes per second to a single partition with WarpStream if you want, because it doesn't have to all go to one node, but you'd never be able to consume it in order. So it wouldn't help you much, but they're still a thing. They're a little bit more virtualized maybe than they are in Kafka, because like if you have 10,000 partitions and you only write to one of them, there's no performance implications or cost for having 9,999 idle partitions, except in our metadata store, there's a number that says you have that many partitions. So there's some benefits there. You don't have to size for the idle partitions, and we don't reserve memory for each partition or anything like that. But they're still, they matter for the data modeling, basically.
So the question, how are you dealing with the lack of built-in mechanism for locking in S3? So how are you handling that? Is it like a single writer, or how are you coordinating that? I probably missed that part.
We have the metadata store I'm talking about is a strongly consistent store that we use that handles basically all of the metadata operations and make sure that they're serializable and strongly consistent. It's super custom. It's not like a thing off the shelf. I don't have time to go into the details in this talk, but that's basically you can think of it as if you're thinking in terms of Kafka terms, it's like the brokers run in the customer's cloud account and we run like KRaft remotely. So kind of it's not KRaft, but it's kind of logically what it is.
Yeah. That explains, because often for that case, for example, some people are using like Dynamo to do the locking, etc. So,
Yeah.
yeah. Thank you.
Hi. Well, this is amazing for me. This is unbelievable what you did. My question is with the produce request, right? In a normal situation, let's talk about Kafka with disk.
Yeah.
The produce request go to, just to simplify, to memory as a dirty pages, and the operating system will take care of the amount of dirty pages stay at bay. If not, it will start throttling, and then produce request will be throttled. So in this case, I'm trying to understand the produce request time. In this case, what you are doing is the produce request will be literally connected to the time it takes to upload this to S3. And you say you are getting 400 milliseconds, correct?
Yeah.
Okay. But that is in general is steady, or
Yeah.
because we have problems with produce requests
Yeah, I mean, it's not like perfectly steady like you're using an SSD, but it's pretty consistent. With S3 Express, it's like butter, like it just doesn't move. With S3 Standard, there's some kind of like temporal, over the course of the day, I'd say about 50 milliseconds of variation at the P99. The way we keep the producer latency low, even with the variability of S3, and this works in every cloud too, is each agent is monitoring the P99 time it takes to flush a file to object storage. Like it just monitors it. And then as soon as a single flush takes longer than the observed P99 over the recent time windows, it just starts another one immediately, like a fast retry. And that has like the number of latency outliers that you get with that, it like dramatically reduced. Okay. The other knob that controls this is the batch, like how long the agents batch. So like with the default of 250 milliseconds, it's optimized for extremely low costs because that's what most people who use WarpStream want. And the P99 there is more like 500 milliseconds. To get the 400, you have to cut it down to like 150 milliseconds or something like that. But
cool. Yeah. Thank you.
But the speculative retries makes a huge difference.
Okay. Thank you very much.
Yeah, thanks for the great presentation. I have questions regarding the consumption progress tracking. Is there any concept like similar to committee offset or consumer group, and how does it implement that?
Yeah, we implement the entire protocol basically except for transactions right now and quotas. The way it works is just, so in Kafka, the offsets are tracked in like a compacted topic. Since we have this like centralized, strongly consistent metadata store, we just track the offsets in that metadata store. And that metadata store also takes care of it acts as the group coordinator basically for the entire cluster. That's how we implement the consumer group protocol. And it also handles all the stuff around idempotent producer. So detecting that like this batch has already been committed and telling the producer that this is a duplicate and not assigning new offsets and all that type of stuff. I realize I'm like hand-waving a lot of stuff with like metadata store. It's just, as talk, can only fit so much stuff on one slide. But yeah, that's basically how it works.
Is the consumer group, like the consumer coordinator, the one that you just mentioned that can handle the hash range generation?
No, the service discovery, so there's the metadata store kind of, which is like handles everything specific. Like there's one logical metadata store for each cluster, and that tracks all the metadata and the offsets and the topics and the batches. The service discovery system is kind of decoupled. That thing is like, it's pretty simple. We don't use Redis. We manually replicate stuff in memory, but you can imagine it as like a triply replicated in-memory data structure. And it's just like all the agents are heartbeating constantly that they're alive and how many cores they have and what AZ they're in. And then that's a data structure in memory that we can just query and be like, okay, what agents are in this AZ? What agents are in this AZ? And we just pipe that down to the agents from the control plane to the agent. And then the agent's like, okay, there's 3 other agents in this AZ. Their node IDs are X, Y, and Z. It sorts them, makes virtual nodes, and just hashes.
So in a normal Kafka cluster, like Apache Kafka, Confluent, etc., if you have a normal Kafka cluster, you can sometimes get busy brokers where some brokers may have a lot of partitions that are busier than other brokers. and you have to use things like cruise control or other things to, make sure the load is evenly distributed. How do you do that with WarpStream?
We just don't. The way that this works is, when I say it that way, I'm trying to find a good picture for this. I think it's this one. Okay, so the way it works is, it's actually configurable. You can choose how it works. But the default way that it works is that when a client connects to WarpStream, depending on how familiar you are with the Kafka protocol, you give it a bootstrap broker, which connects you to like one agent. Then the client goes to that agent and does a metadata request, and it tells it like who's the topic partition leader for each partition. In WarpStream, what we do is we just tell each client that there's one agent that's the leader for all topic partitions. And then the service discovery system ensures that we do essentially global round robin load balancing for each metadata request. And so the net effect is that instead of trying to balance topic partitions, you're balancing client connections. That in practice turns out to work like really well. It's possible for you to have like a single client that's writing like so much data, it causes a hotspot, but like in practice, I've never seen it. Like load balancing clients works really well. If you want it to behave more like a traditional Kafka cluster, you can actually configure on a per client level how the view of the cluster that the client sees. So you can tell WarpStream, hey, I want you to actually assign all the partitions to the agents, like based on their ranges, so that the client actually ends up spreading its load amongst all the agents. I think there's one other strategy, I can't remember what it is. I think it's like hashing versus range. But you can basically pick. Like, you can have it behave more like Kafka if all your partitions are equal, or you can just have it load balance connections like by default. In practice, I've just like never seen, it's pretty hard to have a client that can write more data than a single agent can handle. And then you can always just like, the cool thing about the agents is you add more containers and it just spreads the load. You don't have to like move a bunch of data around, so you can just add more agents temporarily until if you have a temporary spike or whatever.
Gotcha. That makes sense.
Yeah.
Thanks for the presentation. I was wondering if the agents serve both reads and writes, or are they separate?
Yeah, by default, the agents run all the roles, and the roles are basically like produce, consume, and jobs. Jobs being like background compactions and deleting expired files from your bucket. But yeah, you can split them out. So you can like when you start an agent, you can give it a role, and the service discovery system, it gets a little weird because your client has to announce that I would like to only produce data, and another client has to announce I would only like to consume data. So your application has to participate a little bit. And the way we do that is we use the client IDs. But you can set it up so some agents are only allowed to do produce, some agents are only allowed to do fetch, and some agents are only allowed to do like background compactions basically, which allows you to split the roles out and gives you better isolation. The other thing you can do, which is cool, and we just added this, is like you can split the agents into groups in the service discovery system. So you can deploy a pool of agents over here and say this is group 1, deploy a pool of agents over here and say this is group 2, and these two pools of agents will never communicate with each other. And any clients that connect over here, over there, will never see the other agents. And so what that does, it allows you to flex essentially a Kafka cluster across multiple VPCs, across multiple regions, across multiple cloud accounts, as long as you can make sure that each group of agents can access the same object storage bucket, which is usually like way easier than securing a Kafka cluster or like doing VPC peering. You can flex the cluster. So we have a couple people doing that too.
Okay, I guess we can conclude, and you guys can ask any other questions offline. Thank you so much for giving the talk, and thank you so much for attending. Yeah, that's it. Have a good day.